Welcome to the Deep Dive, where we plunge into complex topics, unpack stacks of sources, and really try to unearth the most surprising facts and crucial insights for you. Today, we're diving into a material that is, well, literally woven into the fabric of our modern world. I mean, think about it.
Yeah.
The windows you look through, the screen you might be looking at right now, the bottles in your fridge, it's all glass.
It's everywhere. Absolutely everywhere.
We see it constantly, but how often do we really stop and, consider where it comes from?
It's truly one of those ubiquitous materials we just take completely for granted, isn't it? It seems simple, right? Transparent, hard, maybe a bit fragile.
Yeah.
But its creation is this really intricate dance of, well, ancient craftsmanship and cutting-edge modern science. So if you've ever paused to wonder about the alchemy, that transforms something as humble as sand into this clear, solid thing, well, then this deep dive is definitely for you.
Indeed. Our mission today is to pull back the curtain on this fascinating, ancient yet incredibly precise world of glassmaking.
Right.
We'll break down the whole process, starting from the raw materials dug out of the earth, all the way to the sophisticated, specialized products that fill our homes and our hands. We've meticulously combed through, industry reports, scientific papers on material engineering, historical accounts, really extracting the core insights and those aha moments that will make you genuinely well-informed about this fundamental material.
We'll explore how this seemingly straightforward substance actually emerges from these extreme conditions, really precise chemistry, and some pretty ingenious engineering. It's quite a journey from dirt to dazzling clarity.
So before we jump right in, maybe take a second to consider.
Yeah.
What do you think is the main ingredient of glass? Is it just sand?
Good question to start with.
And if it is, how does that simple ingredient go through such a radical transformation into something so clear, so strong, yet also so delicate? That's the sort of chemical magic we're about to uncover.
Let's get into it.
Okay, so where does this incredible material even begin? It all starts with some of the Earth's most common ingredients, but they have to be meticulously selected and prepared.
Right. And when we talk about glass for everyday items, think bottles, windows, jars, we're primarily focusing on what's called soda lime glass.
Soda lime.
Yeah. It's really the workhorse of the glass world, makes up something like 90% of all manufactured glass out there.
Wow, 90%. So that's most of what we see.
Pretty much. And at its very heart, the primary ingredient, the thing we call the glass former, is silica sand. We're talking about silicon dioxide, SuSiO.
Right, sand.
But, and this is crucial, this isn't just any old sand you'd find on a beach or, in your kid's sandbox.
Oh, okay.
For glass making, this sand has to be incredibly pure and remarkably fine-grained. Picture those pristine white sands you see in deserts, maybe. It's often quarried from very specific geological deposits.
I've always just thought of sand as, well, sand. But you're saying there's a huge difference in quality. What makes certain sands suitable for glass, and why is that purity so critical?
It's a really critical distinction. Ordinary beach sand, for example, often contains a high percentage of iron impurities.
Okay.
And that would give the glass this kind of unwanted greenish tint. Plus, it's got other minerals, bits of shells, organic matter, all sorts of stuff.
Right. Not ideal for a clear window.
Not at all. For high-quality glass, the silica sand needs to be over 99% pure SiOs. Any significant impurities, things like iron oxide, chrome oxide, even bits of alumina or clay particles can severely compromise the clarity, the strength, and even the final color and optical properties of the glass and the fine grain nature. That just ensures a more uniform mixture and a smoother, more efficient melt later on. Silica is the backbone because when you heat it to extreme temperatures, its silicon-oxygen bonds can rearrange into that sort of amorphous, disordered network structure that actually defines glass.
Understood.
Yeah.
So it's not just about getting it to melt, but getting it to melt cleanly, uniformly. But here's the thing I was wondering about. Silica alone has an impossibly high melting point, doesn't it? Like way too high for practical manufacturing.
Exactly, you're spot on. Pure silica melts at over 2,000 degrees Celsius. That's 3,632 Fahrenheit.
Whoa.
Yeah, trying to run a factory at those temperatures would make industrial production just not really feasible, certainly not economically viable.
Right.
So you absolutely need to add something else to bring that melting temperature down.
Okay, so what are these magic ingredients?
That's precisely where our crucial modifiers come into play. Think of them as the chemical helpers that make the silica workable.
Okay.
First up, we have soda ash. Chemically, that's sodium carbonate, not so.
Soda ash, right.
This stuff is absolutely critical because it acts as a flux.
A flux.
Yeah, a flux. It basically disrupts the silica structure just enough to lower its melting point dramatically. Without soda ash, melting silica would demand such extreme energy inputs. I mean, large-scale glass production as we know it would be economically crippling.
Wow.
Soda ash brings that melting point down to a much more manageable 1500 to 1600 degrees Celsius. Still incredibly hot, but achievable. It makes the whole process far more energy efficient and industrially possible. It's really the key to making glass manufacturing practical on a massive scale.
Okay, so soda ash is the melting helper. But if we just had silica and soda ash, would that glass actually be stable? Like, could you use it for a drinking glass or a window, or would there be a catch?
That's a great question, and it points directly to the need for our next key ingredient. Limestone. That's calcium carbonate, cacao.
Limestone, okay.
If you only had silica and soda ash, what's called sodium silicate glass, the resulting glass would actually be quite soluble in water over time.
Soluble, like it would dissolve.
Slowly, yes, it would degrade and eventually dissolve, which is obviously not what you want for a window facing the rain or a bottle holding your drink.
Definitely not.
So limestone acts as a stabilizer and durability provider. It adds crucial chemical stability, rigidity, and makes the glass resistant to weathering. It stops it from slowly dissolving or degrading when exposed to water or humidity over years and years. This is part of the secret, actually, behind the remarkable longevity of ancient glass artifacts that archaeologists still dig up today.
Fascinating. So it's the secret sauce for making it last.
Yeah.
That really puts the survival of those ancient glass pieces into perspective. Okay, and then we have aluminum. Aluminum oxide, aluro, what's its specific role in this chemical cocktail?
Alumina is added in smaller quantities, usually just between 1% and 3%, but it plays a really vital role in enhancing the glass's overall durability, its hardness, and its resistance to chemical attack and weathering.
Okay.
I mean, think about how glass is exposed to the elements, sun, rain, big temperature swings, even just everyday detergents when you wash things.
Right.
Alumina helps the glass maintain its integrity against all that environmental degradation, and it also has a neat side effect. It improves the glass's viscosity, how thick it is at high temperatures. That makes it a bit easier to form without causing defects like unwanted crystallization when it starts to cool down.
Okay, so we've got the core ingredients.
Yeah.
Silica, the former, soda ash, the melter, limestone, the stabilizer, and alumina, the resistor, each with a very specific, carefully balanced role. But here's where the ingenuity really kicks in and where the industry shows its incredible resourcefulness.
Yeah.
Cullet,
Yes, cullet.
which is just recycled glass.
Yeah.
Why is it such a powerful addition to the mix beyond just, the obvious environmental benefits?
Cullet is amazing. Its secret power isn't just about being eco-friendly. It's a profound energy multiplier. Think about it this way. Virgin raw materials, like sand and soda ash, need to undergo a complete chemical transformation in the furnace, right?
Mm-hmm.
They have to absorb enormous amounts of energy to convert from their raw mineral forms into that glass structure. Cullet, however, is already glass. It's already done that transformation. It's already formed those silicon-oxygen bonds. So when you add cullet to the raw batch, it doesn't need to chemically transform, it just needs to melt and flow. It's like reheating a pre-cooked meal instead of cooking from scratch.
Right, so it melts much easier.
Much easier. It melts at a significantly lower temperature, roughly 20 to 30 degrees Celsius lower for every 10% cullet you add, and much, much faster than the virgin raw materials.
So it's like giving the whole melting process a jump start, a real shortcut to industrial scale efficiency.
Exactly. And this directly translates into massive energy savings in the furnace. The estimates suggest something like a 2 to 3% energy reduction for every 10% of cullet used.
Wow.
Plus, obviously, it conserves natural resources, less sand, soda ash, and limestone needing to be mined. And it reduces emissions too. It's just an incredible example of a circular economy in action. Many modern glass factories now use up to 90% recycled material in their production.
90%. That's astonishing. Imagine 9 out of 10 parts of a new glass bottle could have come from an old one.
It really is remarkable. It highlights how circular and genuinely sustainable glass production can be. It's kind of a model for other industries in terms of minimizing waste and maximizing resource use.
Definitely. And beyond these core components and this super important cullet, we can also fine-tune the glass for specific needs with optional additives, can't we? Like for color or other properties?
Precisely. These are usually added in much smaller quantities, really just to tweak the final product. For instance, if you see that subtle green tint in some bottles, maybe some wine bottles or older style soda bottles,
Because I know the one.
that's often due to iron oxide. Sometimes it's just a natural impurity lingering in the sand if the purity isn't absolutely top-notch. Other times it's actually intentionally added for a specific aesthetic look.
Okay, and then there's its surprising counteragent, manganese dioxide. You mentioned iron oxide causes a green tint. Is there anything that can undo that? Or are you just stuck with green glass if there's iron?
Ah, good point. That's where manganese dioxide comes in. It's a rather clever bit of chemistry, actually. Manganese dioxide is used specifically to remove those unwanted greenish or brownish tints caused by iron impurities.
Really?
It essentially neutralizes the color effect of the iron, making the glass much clearer and more transparent. It oxidizes the iron, changing its color absorption properties. It's a chemical balancing act to achieve that really pristine clarity we expect in most glass.
Clever.
And then for really high-end stuff like fine crystal glass, fancy tableware, vases, that sort of thing, lead oxide has traditionally been used. This gives the glass incredible brilliance, that real dazzling sparkle you associate with crystal. It also makes the glass significantly softer and easier to cut, engrave, and polish into those intricate designs.
Ah, so that's why crystal cuts so well.
Exactly. Though it's worth noting, due to health concerns around lead, lead-free crystal alternatives are increasingly common now. They often use things like barium, zinc, or potassium oxides instead to get similar brilliance and workability.
Interesting. So next time you pick up a bottle or admire a fancy crystal glass, you can truly appreciate that it's not just some generic material. It's actually a carefully engineered concoction, a specific recipe, tailored precisely for its purpose.
Absolutely. Every component is there for a reason. And that meticulous engineering doesn't stop at just picking the ingredients.
Which brings us neatly to our next crucial stage, the recipe precision itself. This is known as batch preparation. So we've talked about all these incredible ingredients, each with a specific job, but simply having them isn't enough, is it? The precision of how they're measured and mixed is apparently paramount.
Oh, absolutely. It's kind of the unsung hero of consistent glass quality. You can think of it like baking, but on a massive industrial scale.
Right.
If you don't precisely measure your flour, sugar, and baking powder, your cake just isn't going to turn out right, is it? It might be too dense or crumbly or flat.
Yeah, I've had that happen.
Same goes for glass. Uniform melting and getting a consistent chemical composition in the final product depend entirely on accurate batching. Any slight variation, even a tiny bit too much of one thing or not enough of another, can lead to defects, internal stresses, or even a completely unusable product down the line.
And in modern glassmaking, this isn't just someone eyeballing it with a scoop, right? The source material really highlights that these are highly automated systems, measuring precisely by weight, not volume.
Oh, absolutely. These are state-of-the-art facilities. They use computer-controlled systems, often involving things like load cells and laser sensors, to measure each ingredient's sand, soda ash, limestone, alumina, cullet, any additives with astonishing accuracy. We're talking down to fractions of a percent by weight.
Wow.
This ensures that the exact proportions defined in that specific glass recipe are maintained for every single batch consistently, 24 hours a day, 7 days a week.
Okay, so super precise weighing. Then what?
Once weighed, the ingredients are then thoroughly blended together. This typically happens in these huge rotating drums, kind of like giant cement mixers, or on sophisticated conveyor belt systems that continuously tumble and mix the materials as they move along.
Right.
The goal here is homogeneity. You want every tiny particle of silica, soda ash, limestone, and everything else to be uniformly distributed throughout the entire mix. Imagine billions upon billions of microscopic particles needing to be perfectly integrated. This ensures that when it hits the furnace, it melts evenly and forms a flawless, consistent glass structure.
So it's all about making sure there are no pockets of unmixed ingredients or areas that are too rich in one component, because that could lead to hot spots or inconsistencies later on.
Exactly that. You need perfect uniformity. And after this meticulous blending, it's not immediately checked into the furnace, is it? There's a step in between.
Correct. The prepared batch, this perfectly mixed powder, is typically conveyed up to and held in temporary storage silos or hoppers. These are usually located just above the melting furnace. These silos basically act as holding tanks, ensuring a continuous and consistent feed of the prepared batch mixture into the furnace. This steady, uninterrupted flow and consistent composition are vital for maintaining stable furnace conditions and enabling the continuous glass production that modern factories rely on. This raises a pretty important question then. What happens if the batch isn't perfectly mixed? Or if those precise proportions are slightly off for some reason? What are the real-world consequences of imprecise batching in such a sensitive process?
Well, if the batch isn't perfectly mixed or if the proportions are incorrect, you can basically anticipate a cascade of problems that will ripple right through the entire production line.
Oh dear.
For starters, you might get areas within the melt that don't melt properly or fully react. This can lead to tiny, unmelted bits of raw materials, often called stones or knots, getting trapped within the final glass product.
Ah, so you'd actually see bits in the glass.
You could, yeah. And they're not just unsightly, they create points of weakness where the glass is much more likely to crack. Furthermore, the chemical composition across the glass won't be uniform.
Right.
This can lead to significant internal stresses building up within the glass as it cools down later. This might not be immediately visible, but it makes the glass considerably weaker, far more prone to cracking or shattering unexpectedly with even minor thermal shock or a small impact.
Okay.
And in really severe cases, a poorly mixed or incorrectly proportioned batch can even lead to a failed melt altogether. That means halting production, cleaning out the furnace. It wastes immense amounts of energy and raw materials. It just underscores how absolutely foundational this seemingly simple mixing step is to the integrity and quality of the final glass.
It really is the science of precision before the fiery alchemy even begins. And speaking of alchemy, that takes us right to the very heart of the process.
Yeah?
Melting. This is where those solid raw materials finally undergo their dramatic transformation into molten glass.
This is truly the alchemical crucible, the fiery heart of it all. The precisely prepared batch mixture is fed continuously into these massive furnaces, and this is where the materials are subjected to just astonishingly extreme temperatures.
How loud are we talking?
We're talking about heating the materials consistently to around 1600 degrees Celsius. That's about 2912 degrees Fahrenheit.
Wow. That's hard to even imagine.
It really is. To put that into perspective, that's hotter than molten lava flowing from a volcano, nearly twice the temperature of a typical ceramic kiln, and actually getting quite close to the surface temperature of the sun.
Incredible.
The sheer amount of energy involved in just maintaining those temperatures 24 hours a day, 7 days a week, in furnaces that can be the size of a small house, is absolutely immense.
And these furnaces themselves, they aren't just built from ordinary bricks, are they? They have to be engineering marvels, constructed from specialized materials.
Absolutely. They're lined with specialized refractory bricks. These are amazing materials, often ceramic-based, designed with incredible precision to withstand not only that intense, continuous heat, but also the corrosive chemical nature of molten glass without melting or degrading themselves. They have to last for years under these conditions.
Right.
The furnaces themselves are typically powered by natural gas, fuel oil, or increasingly electricity, especially for cleaner operation or specialized glass types. It depends on the region, the cost of energy, and the scale of the factory.
And this melting, it's not a quick zap, is it? How long does it take for the raw materials to actually become molten glass?
No, it's definitely not quick. A single batch of material might take anywhere from 12 to even 24 hours, or sometimes longer, to fully melt and homogenize within the
A
furnace.
sole day. Wow.
Yeah, and it's not just about liquefying the materials, it's about ensuring complete homogeneity. Every single part of that glowing molten liquid must be perfectly consistent throughout its entire volume. All the ingredients need to fully dissolve into each other at a molecular level.
So it's not just melting it, but thoroughly blending it while it's incredibly hot.
Mm-hmm.
And during this stage, there are critical chemical reactions happening, right? It's not just a physical change from solid to liquid. The soda ash, for instance, you mentioned, it breaks down.
Yes, absolutely. These chemical reactions are the very essence of glass formation. The soda ash, the sodium carbonate, it decomposes under the heat, releasing carbon dioxide gas. This is actually where a significant amount of the initial bubbling in the melt comes from.
Oh, yeah.
But more importantly, the sodium oxide left behind then reacts with the silica to form sodium silicate. That's a fundamental building block of the final glass structure. Similarly, the calcium carbonate from the limestone also decomposes, releasing more KO, and the resulting calcium oxide integrates into the evolving silicate network, providing that crucial stability we talked about.
So what does this all mean for the glass itself? These reactions aren't just like side effects, they're critical for the material we end up with.
They are absolutely critical because they're directly responsible for forming the actual glass structure. It's during these high-temperature chemical transformations that the individual raw material components dissolve into each other and start linking up to form that characteristic disordered amorphous network of silicon and oxygen atoms interspersed with sodium and calcium that defines glass. Without these specific reactions happening correctly, you simply wouldn't get glass as we know it.
Okay.
The release of gases, like sea aero, while it creates bubbles that need to be dealt with, is actually a natural and necessary part of this profound chemical alchemy taking place in the furnace.
Bubbles, a natural consequence, as you said. But obviously, you don't see bubbles trapped in your window pane or your drinking glass. So how on earth are those pesky bubbles removed from such a viscous, glowing, hot liquid? That seems like a monumental challenge.
It does, doesn't it? But what's truly ingenious here is how they manage this, through a process called fining, or sometimes refining.
Fining.
As you noted, the chemical reactions release gases, creating bubbles of various sizes throughout the melt. Now, some of the larger bubbles will naturally rise to the surface and escape just due to buoyancy, like bubbles in boiling water.
Right.
But the smaller, more stubborn ones, the microbubbles, those are the most problematic for clarity and strength. They need some help to get out.
How do they do that?
The process is often aided by adding small quantities of special refining agents to the batch. Things like sodium sulfate or antimony oxide are common. When these agents get hot in the furnace, they also decompose and release gases. But here's the clever part. These intentionally released gases actually absorb the smaller existing bubbles from the melt. They cause them to coalesce, to merge together into larger bubbles.
So they make big bubbles out of little ones.
Exactly. And once those bubbles become larger, they rise much more rapidly to the surface due to the increased buoyancy, where they can burst and escape, leaving behind a perfectly clear, bubble-free molten glass. This also requires extended heating time within the furnace, often in a dedicated, slightly hotter fining zone, to give those bubbles sufficient time to form, rise, and escape before the glass moves on and starts to cool.
So it's a careful combination of chemistry and time, ensuring that purity down to the microscopic level.
Yeah.
And once all that's done, the melting, the reacting, the fining, you're left with this final molten state. What's it actually like visually, or in terms of its consistency at this point?
At this stage, after spending many hours in the intense heat of the furnace, it's a truly mesmerizing sight. You have this highly viscous liquid glowing intensely red hot, with the consistency often compared to thick honey or maybe warm treacle.
Thick honey, okay.
It's perfectly uniform now, completely clear of bubbles and unmelted particles, and absolutely prepared for its next grand transformation, being shaped into something useful.
All right, so we have this incredible molten, honey-like liquid, perfectly uniform, bubble-free. But before it can take its final shape, it sounds like it needs a bit more finessing.
Right.
That's where fining and conditioning come in, right? Preparing it precisely for its grand transformation into a specific product.
That's absolutely right. While a lot of that crucial bubble removal, the fining, happens during the main melting stage, it's often revisited or finalized here in the conditioning stage.
Right.
This is really about ensuring absolute crystal clarity, which is essential for most glass products we use. Any remaining tiny bubbles, even microscopic ones, would compromise the glass's optical quality, making it less transparent, maybe creating distortions, or even just making it weaker.
Right.
So those fining agents we talked about, like sodium sulfate, might still be active here, acting as catalysts to help any last stubborn microbubbles combine and escape. It's really about achieving near perfection in transparency before it gets shaped.
So it's not just about getting rid of most bubbles. It's really about achieving that optical precision, that pristine clarity we expect in, say, a window or a camera lens. Okay, and then once it's perfectly clear, it moves into the conditioning zone. What happens there? Is it just cooling down?
It's much more than just cooling down randomly. In the conditioning zone, the molten glass undergoes a very carefully controlled, gradual reduction in temperature. It needs to come down from its extreme melting temperature, remember, 1600 degrees C or so, down to a workable temperature range for forming, which is typically around 1100 degrees or about 12 degrees Fahrenheit.
Still pretty hot.
Still incredibly hot, yes.
Yeah.
But this isn't a rapid drop. It's a precise incremental cooling process. But the absolutely crucial part here is achieving perfect temperature uniformity. It's not enough for the average temperature across the glass to be right. The temperature throughout the entire mass of molten glass from the center to the edges, top to bottom, must be meticulously consistent.
Why is that temperature uniformity so critical at this specific point? What are the consequences if one part of the molten glass is hotter or cooler than another as it heads towards being shaped?
Well, if the temperature isn't perfectly uniform throughout that viscous molten glass, it immediately starts creating internal stresses within the material even before it solidifies.
Huh.
Imagine one part of the thick honey-like glass flowing just a bit slower because it's slightly cooler, while another part nearby is still hotter and therefore more fluid, flowing faster. This differential viscosity, this uneven flow and subsequent cooling creates tension and compression forces within the material itself.
Okay.
This internal stress, if it's not managed and eliminated at this stage, gets locked into the glass as it cools further. It significantly weakens the final product, making it much more prone to cracking or shattering later on with even minor impacts or subsequent temperature changes during use.
Right.
It's kind of like a chef meticulously cooling a delicate sauce or custard to the perfect temperature and consistency before plating it. The quality, the texture, the stability of the final dish, or in our case, the glass product, depends entirely on this meticulous temperature control in achieving perfect homogeneity right before the final shaping step. It's the final, precise preparation before it takes its definitive form.
That analogy makes perfect sense. It sounds like this invisible, delicate dance of physics and chemistry happening inside that glowing liquid. And speaking of definitive forms, that leads us directly into the next stage, forming, where the real art of transformation happens and the molten glass finally gets its distinct shape. And this part, as you hinted, is incredibly diverse, because the method varies wildly based on what the glass is ultimately going to be used for.
This is absolutely where the sheer ingenuity of glassmaking really comes to life. We're transforming that uniform, viscous liquid into all the recognizable glass objects that populate our daily lives. And one of the most common and frankly truly impressive methods, especially for producing huge quantities of large, flat sheets of glass think windows, mirrors, maybe even some solar panels, is the float glass process.
Ah, the float process. Okay, here's where it gets truly amazing based on our research. The molten glass is literally poured out and then floated across a vast flat bed of molten tin. That sounds almost impossible to manage. Why on earth tin?
It does sound completely counterintuitive, doesn't it? Like trying to float water on top of mercury or something.
All right.
But tin is very cleverly chosen for several critical reasons.
Okay.
Firstly, tin has a high density, much higher than molten glass, which allows the glass ribbon to float perfectly on its surface without sinking. Secondly, and this is absolutely critical, tin doesn't chemically react with the hot glass, so it doesn't contaminate it or stick to it as the glass cools. And perhaps most importantly, the surface of the molten tin is naturally perfectly flat and level due to gravity. Imagine a vast, shimmering liquid mirror. Because of this, gravity itself naturally spreads the molten glass evenly across the tin surface into an incredibly uniform, smooth, and parallel-sided sheet. This process creates glass with a degree of optical clarity and flatness that would be practically impossible, or at least incredibly expensive, to achieve through mechanical grinding and polishing alone, especially on the massive scale required for architectural glass.
So it's kind of the simplest yet most elegant and effective way to achieve perfectly flat glass, just leveraging the basic laws of physics.
Exactly. It's genius in its simplicity. The ribbon of glass then slowly cools and solidifies as it moves along this long bath of molten tin. This happens in a carefully controlled inert atmosphere, usually nitrogen and hydrogen, to prevent the hot tin from oxidizing. As the glass cools, its viscosity increases, and eventually it becomes solid enough to be lifted off the tin bath onto rollers without sagging or deforming. What comes off the end is what's known as annealed float glass. It's truly incredible to visualize this continuous liquid-on-liquid process, creating something as seemingly mundane and solid as a giant sheet for a window pane, which is then cut into huge pieces for buildings, cars, furniture, all over the world.
Just incredible to picture that. Now, for something completely different in shape, like your everyday soda or beer bottle, that uses a different process called the blow-and-blow process. How does that work, and what are the specific challenges in creating those precise, hollow shapes consistently?
Right. For bottles and other containers with narrow necks, the process starts with a precise gob, G-O-B, which is essentially a measured droplet or lump of molten glass. This gob is cut cleanly by shears as it falls from the feeder and drops into a preliminary mold, often called the blank mold.
Okay, blank mold.
Air is then blown into this gob, not to fully shape the bottle yet, but to create a preliminary shape called a parison, or sometimes a preform. The parison is basically a rough version of the final bottle. Usually the neck finish where the cap goes is fully formed at this stage, but the body is still somewhat bulbous and thick-walled.
Right.
This parison is then quickly inverted and transferred mechanically to a second, final mold known as the blow mold. Air is then blown into it again, this time with higher pressure, to expand the parison fully against the contours of the final mold, achieving the complete desired shape of the bottle.
2 blows. Makes sense.
Exactly. It's a very rapid, high-speed, and high-volume process. Modern machines, often rotary machines with multiple molds, are capable of producing hundreds of bottles per minute. The main challenges are ensuring a uniform wall thickness throughout the bottle, you don't want weak spots, and achieving very precise neck finishes so that the caps seal perfectly later on.
And closely related but distinct is the press and blow process. You mentioned this is usually for jars and wider mouth containers. What's the key mechanical difference there compared to the blow and blow method?
The key difference lies in that initial shaping step, how the parison is formed. In the press and blow process, instead of using compressed air to initially shape the gob in the blank mold, a mechanical plunger actually descends and presses the molten glass against the walls of the blank mold.
Ah, a physical press.
Yes. This pressing action forms the initial parison. This method is particularly effective for creating wide-mouthed items like food jars, where you need a very precise and consistent opening or finish, or for items that might have more intricate internal details near the base. After this initial pressing forms the parison, it's then transferred to the blow mold, and compressed air is used to finalize the shape, stretching the glass to the final mold's dimensions, similar to the second stage of the blow and blow process.
Okay, so one relies more on an initial mechanical push for the parison, the other relies on an initial puff of air. Got it.
Precise.
But that's still not the end of the line for different glass forms, is it? We can even make glass fiber, like for home insulation or even textiles. That's always seemed like a surprising fact to me. How on earth do you turn rigid, brittle glass into a flexible fiber? It seems totally counterintuitive.
It really does, but this is another remarkable application that truly showcases the versatility of glass. For making glass fiber, molten glass, usually a specific formulation designed for fiberization, is allowed to flow down through the base of a special furnace called a bushing. This bushing base is perforated with thousands of incredibly tiny nozzles or holes.
Thousands.
Yes, thousands. Almost like a giant, very precise shower head made of platinum alloy to withstand the heat. The molten glass is extruded through these tiny nozzles, forming extremely thin, continuous filaments or threads. These can be as thin as a human hair, or often even much finer, down to just a few microns in diameter. These incredibly fine threads are then rapidly cooled, almost instantaneously, by jets of air or sometimes water spray, immediately after they emerge from the bushing. This rapid cooling is crucial. Then, the solidified fibers are gathered together into strands and often wound onto large spools or drums, much like textile yarn.
And that makes them flexible.
What's fascinating is that while bulk glass is indeed rigid and brittle, when you draw it down into these incredibly fine filaments, it becomes surprisingly flexible and also possesses very high tensile strength relative to its size. Think about it like a single thick stick versus a bundle of thin twigs. The bundle can bend much more easily. It's the same principle. The thinness allows for flexibility.
That's truly amazing. And it has such diverse applications, doesn't it?
Well-
From the pink, fluffy stuff insulating our attics,
Exactly. Fiberglass insulation.
to specialized textiles used in things like circuit boards or even heat-resistant fabrics. And of course, fiber optics, which are ultra-pure glass fibers carrying our internet signals around the globe at the speed of light.
Precisely. It's an astonishing transformation of the material. So once the glass has taken its shape, whether it's a flat sheet, a bottle, or a fiber, it's beautiful, it's clear, it's got its form. Is it ready to go then? Or is there still another critical step before it's actually strong and usable in the real world?
Not quite ready. In fact, right after forming, regardless of the method used, the glass is actually in its most vulnerable state.
Oh,
Yes, it's incredibly brittle at this point and absolutely brimming with internal stresses locked inside it. This brings us to a massively crucial, non-negotiable step for ensuring its strength and long-term durability.
annealing.
Annealing. Okay, so what exactly is the problem if we just let the hot glass cool down naturally in the air after shaping it? What makes it so incredibly brittle at that specific point?
The problem lies fundamentally in glass's unique characteristic as an amorphous solid. Unlike a crystalline material like metal or salt, where atoms arrange themselves in a nice, orderly, repeating lattice structure as they cool.
Glass molecules solidify in a random, disordered arrangement, much like a liquid. Now, when molten glass cools rapidly, as it does right after forming when exposed to room temperature, the outer layers cool down and solidify much faster than the inner layers.
Okay, outside cools first.
Exactly. So imagine the outer skin of the glass trying to shrink and contract as it cools and hardens, while the inside is still hot, expanded, and relatively more fluid. This differential cooling, this uneven contraction between the surface and the core, locks in immense internal stresses. Think of them as invisible tensions and compressions, pulling against each other deep within the glass structure.
Like a tightly wound spring inside the glass.
That's a perfect analogy. These stresses make the glass extremely prone to shattering with even the slightest mechanical impact, a minor scratch, or even just a small, rapid temperature fluctuation. You'd have products that would just spontaneously crack or fall apart sitting on a shelf or during shipping. It's basically uselessly fragile without annealing.
Okay, so annealing is the solution to carefully unwind that internal spring, essentially, release those stresses, and it involves cooling the glass very, very slowly.
Precisely. To eliminate these destructive internal stresses and make the glass strong and usable, the newly formed glass pieces are carefully moved through a long, tunnel-like controlled furnace known as a lair. That's L-E-H-R, pronounced leer.
The lair, okay.
Inside the lair, the glass is first gently reheated to its specific uniform temperature. This temperature is just below its softening point for typical soda lime glass. That's around 600 degrees Celsius, or 1112 Fahrenheit. Holding it at this temperature allows the glass molecules enough mobility to relax just slightly, to rearrange themselves and release those dangerous internal strains that built up during the initial rapid cooling.
Okay, so it relaxes the stress. Then what?
Then, the temperature inside the lair is not just lowered, but it's lowered very, very gradually, following a precisely engineered temperature profile, cooling slowly over different zones within the lair until the glass finally emerges at the other end at or near room temperature.
And this isn't a quick trip through the tunnel, is it?
No, definitely not. Depending on the thickness of the glass and its specific composition, this annealing process can take several hours, sometimes even days, for very thick architectural glass or complex optical components.
Wow. Why does that slow, controlled cooling make such a profound difference? What's actually happening at the molecular level during this long, slow cool down in the lair?
This slow, controlled cooling is the key. It allows all parts of the glass, the surface, the core, everywhere, to cool down and contract at a much more uniform rate. It gives the glass molecules sufficient time to relax and settle into a more stable, lower energy, stress-free configuration as the entire piece solidifies together.
Okay.
It essentially gives the material time to adjust uniformly to the temperature changes, distributing any residual internal stresses much more evenly and at a much lower level throughout the entire piece, rather than having those dangerous high stress points.
Right.
This process is absolutely vital. It prevents future cracking. It dramatically improves the glass's overall mechanical strength and durability, making it tough enough for everyday use, and it significantly enhances its resistance to thermal shock, meaning it can handle reasonable temperature changes without breaking. Without proper annealing, almost all glass products would be far too fragile for almost any practical application.
It sounds analogous to tempering steel to make it stronger, or even, like you said, letting a cake or a loaf of bread cool slowly on a wire rack to prevent it from cracking or collapsing when you take it out of the hot oven too fast.
Exactly. It's a fundamental principle of material science applied perfectly here. It's all about managing those internal forces that arise during cooling to achieve a stable, robust, and usable final product.
A critical step for sure.
So the glass has been formed into its shape. It's been carefully annealed in the lair to give it strength and stability. But before it gets packed up and shipped out the door, there's one more crucial stage: inspection and quality control. Now, in modern glassmaking, a lot of this is highly automated, but rigorous inspection is absolutely essential to meet the incredibly high standards required, and importantly, ensure product safety and performance, especially given the sheer scale of production.
Absolutely. The goal is perfection, or really as close to it as is physically and economically possible, especially when you're making millions of bottles or square meters of window glass. There are several layers to the inspection process.
Okay.
Visual inspections, for instance, are still critical, even with automation. High-speed cameras coupled with sophisticated machine vision software, sometimes still augmented by trained human inspectors for particularly complex shapes or subtle defects, are continuously scanning the glass. They're looking for any remaining imperfections like tiny bubbles, often called seeds or blisters, that might have escaped the fining process.
Right.
Or subtle streaks or lines in the glass, known as cords, which indicate incomplete homogenization. They also look for any distortions that could affect clarity or visual appearance, or any surface blemishes like scratches or chips picked up during handling.
And beyond just what you can see, there are also mechanical tests performed, right?
Yeah.
To assess its actual structural integrity and physical properties.
Yes, absolutely. Depending on the product and its intended use, various mechanical tests are performed, often on a statistical sampling basis. They might check for residual internal stress, specifically to ensure the annealing process was successful and the glass is stable and stress-free. They measure the overall strength of the glass, perhaps its resistance to impact or pressure. For containers like bottles, they might test things like vertical load strength, how much weight it can take stacked on top, or internal pressure resistance, burst strength. And they measure the precise thickness and dimensional accuracy, which is particularly important for things like float glass that need to be perfectly uniform across vast sheets, or for components that need to fit together precisely.
And for really specialized applications, like the glass used in camera lenses, microscopes, or maybe high-tech electronic displays, I imagine the optical testing becomes absolutely paramount.
You're exactly right. For any application where pristine clarity and specific optical properties are critical, very sophisticated optical testing is performed. This uses lasers, interferometers, and other advanced instruments to ensure the glass transmits light correctly without unwanted scattering, absorption, or aberrations. They check for things like refractive index uniformity, lack of distortion, and birefringence, which indicates internal stress. Think about a high-definition TV screen, a precision scientific lens, or the fiber optic cables carrying data. Every single millimeter of that glass needs to perform flawlessly from an optical standpoint.
Now, inevitably, some pieces won't pass muster. What happens to the glass that gets rejected during these rigorous inspections? Is it just discarded as waste, adding to landfill problems?
Well, what's really fascinating here, and speaks again to the efficiency of the industry, is that defective glass pieces are very rarely just wasted in modern glass manufacturing. This is where the inherent circularity of glass really shines once more. Most often, these rejected pieces, whether they're bottles, jars, or offcuts from flat glass, are simply crushed and recycled directly as cullet. They get fed right back into the beginning of the process, mixed in with the next batch of raw materials heading to the furnace.
Closing the loop again.
Exactly, closing the loop perfectly and significantly reducing waste. Now, if for some reason the rejected glass isn't suitable for remelting into new high-quality glass products, perhaps it has a specific type of contamination or coating that's hard to remove, it might still be crushed and repurposed for other, less demanding industrial uses.
Like what?
Things like being used as aggregate in roadbeds or construction materials, as an abrasive material for sandblasting, or even incorporated into things like decorative tiles or filtration systems. Very little actually needs to go to landfill.
That really highlights the incredible efficiency and resourcefulness of the modern glass industry. It's not just about making perfect glass, it's also about minimizing waste and maximizing the utilization of resources at every single step of the way.
It's a true testament to how mature and highly optimized the glassmaking process has become over literally centuries of development. The industry has really perfected the art of lean manufacturing and resource recovery in a way many other industries could learn from.
Absolutely. And once the glass has passed all its rigorous inspections, it's finally ready for its final transformation. The cutting, coating, and finishing touches. This is really where it goes from being a basic, albeit strong and clear, material into a highly functional and specialized product tailored precisely for its specific end application. It's truly the bridge from a raw sheet or bottle to a high-tech component or a finished consumer good.
Indeed. This stage adds enormous value and functionality. For flat glass, for example, like those large sheets produced by the float process destined for windows or display screens, the very first step after annealing and inspection is usually precise cutting.
Right.
Massive automated machines, often using diamond-tipped cutting wheels or sometimes even high-power laser technology, accurately score the glass surface. Then, controlled pressure is applied to cleanly break the glass along the score lines into custom sizes and shapes, whether that's for architectural window panes, automotive glass pieces, mirrors, or the small rectangles needed for smartphone panels.
And then, beyond just cutting, for clarity or aesthetics or safety, things like polishing and beveling might come into play, or even drilling holes for specific mounting needs.
Exactly. Further polishing can be used to enhance optical clarity even more, or to create a perfectly smooth reflective surface, especially if it's going to be coated for mirrors or used in high-end architectural glass. Beveling, which is creating an angled or rounded edge, is often done for aesthetic appeal, like on glass tabletops or decorative mirrors, or sometimes simply to create a safer, less sharp edge, maybe on glass shelves or shower doors. And yes, holes can be precisely drilled using specialized diamond bits for hinges, handles, or mounting fasteners.
But perhaps the most transformative part of this stage, especially for flat glass, are the specialized coatings you can apply.
Oh, absolutely. A vast array of incredibly thin film coatings can be applied to the glass surface, usually in sophisticated vacuum deposition chambers. These coatings are often only nanometers thick, but can fundamentally change the glass's properties. Think about your smartphone screen again. It almost certainly has an anti-reflective coating to reduce glare and improve visibility, and likely also a hydrophobic, water-repelling, or oleophobic, oil-repelling coating to resist fingerprints and smudges, making it easier to keep clean.
Right. And you also see those energy-efficient windows in modern buildings that claim to block heat or UV rays. That's coatings, too.
Precisely. There are specialized coatings that block harmful ultraviolet UV radiation, protecting interiors from fading. There are low emissivity or low E coatings, which are incredibly clever. They reflect infrared heat back towards its source, so in winter they help keep heat inside the building, and in summer they help keep external heat out, significantly improving insulation properties and reducing energy costs for heating and cooling.
Wow.
There are even electrochromic or smart tint films that can change their opacity or tint when a small electrical voltage is applied, allowing you to dynamically control the amount of light and privacy through the window. These coatings add incredible, often completely invisible functionality to the basic glass sheet, fundamentally altering its performance for specific needs.
That's amazing technology. And for bottles and jars, what kind of final touches do they typically get before they're ready to be filled with your favorite beverage or food product?
For bottles and jars, after they come out of the lair and pass the initial bulk quality control, they usually undergo final, even more detailed automated inspection, again, using high-speed machine vision systems. These systems are incredibly fast and accurate, checking for any last-minute critical defects like small cracks, called checks, chips around the rim, the finish, or any foreign particles, inclusions, before they head to the packaging line.
Okay.
Customization is also a big part of this final stage for containers. Labels, brand logos, or textured decorative patterns can either be molded directly into the glass surface during the forming process itself, giving it a permanent, premium, embossed, or debossed look, or they can be applied later. This might involve high-speed screen printing, applying adhesive paper or plastic labels, or even ceramic enameling, where colored glass frit is printed on and then fired onto the surface for maximum durability, like you see on some beer bottles. Finally, the finished, inspected, and possibly decorated products are meticulously arranged, often shrink-wrapped or placed in cartons, palletized, and prepared for shipping to the beverage company, food processor, or retailer, ready for their ultimate purpose.
So what does all this mean for us, the end users, the consumers? It really means that the seemingly simple bottle we drink from, or the window pane we look through, or the screen we tap on, has actually gone through these incredible, often invisible, layers of processing, inspection, and customization to become the highly specialized and reliable product it is. From a basic raw sheet of float glass to a high-tech multi-coated smartphone screen or an energy-saving architectural window, this final finishing stage truly transforms the material from a generic substance into a highly functional component, perfectly designed to integrate seamlessly and perform effectively in our daily lives.
It's absolutely the critical final bridge. It takes the strong, clear, annealed glass and turns it into a highly specialized, value-added product that performs specific functions we now completely rely upon, often without even realizing the sheer amount of technology and precision involved in getting it there.
And speaking of specialized products, that brings us perfectly to our final main section. We need to dive beyond the basics of soda-lime glass into some truly remarkable, specialized glass types. Because, as we've hinted, glass isn't just one single material, it's really a whole family of materials. Each member has vastly different properties achieved through tweaking those chemical compositions and employing unique processing methods. This is really where glass becomes a kind of miracle material, engineered to withstand extreme conditions or perform amazing feats.
This is absolutely where material science gets exciting and pushes the boundaries of what we thought was possible with glass. Let's start with one you likely interact with, maybe dozens or hundreds of times every single day, often without giving it a second thought. Gorilla Glass, the stuff used in the screens of most smartphones, tablets, and even some smartwatches and laptops.
Right. This stuff is incredibly tough compared to older screens. I remember when phone screens seemed to shatter just by looking at them the wrong way. Now they can survive so much more abuse. What's the key feature here? What makes it so remarkably resilient to scratches and impacts?
Its key feature, its secret weapon, is that it's chemically strengthened. This is achieved through a really fascinating process called ion exchange.
Ion exchange, okay.
Essentially, after the glass is cut and shaped to the size of the phone screen, it's submerged in a bath of hot molten salt. Typically, it's potassium nitrate at temperatures around 400 degrees Celsius or 752 Fahrenheit. Now, during this immersion, which can last several hours, something amazing happens at the atomic level. Smaller sodium ions that are naturally present within the surface layers of the glass literally diffuse out of the glass and into the molten salt bath. At the same time, larger potassium ions from the salt bath diffuse into the glass surface to replace those departing sodium ions.
So bigger ions are squeezing into the spots left by smaller ones.
Exactly. These larger potassium ions are essentially being stuffed or jammed into the spaces vacated by the smaller sodium ions within the rigid glass network structure. When the glass cools down, these larger ions create a powerful layer of compressive stress on the surface of the glass. They're basically pushing outwards, but constrained by the glass structure, creating an inward force.
So it's like the surface is under constant tension, like a molecular level force field, constantly pushing inward against any potential damage.
Yeah.
That's incredible.
Precisely. It's like putting armor plating on the glass at the atomic scale. This deep compressive stress layer acts as a protective shield. Any external force trying to damage the glass, like an impact from a drop, or the pressure from a sharp object trying to scratch it, has to first overcome this pre-existing compression before it can even begin to initiate a crack or break the glass surface.
Ah, okay.
This makes Gorilla Glass incredibly tough, highly scratch resistant, and significantly more durable against drops and impacts compared to ordinary unstrengthened glass, which is exactly why your phone screen can generally take quite a beating these days and still look remarkably pristine. It's truly amazing that the screen you might be looking at right now is likely made of this very material, a testament to some really clever, subtle chemical engineering.
Absolutely mind-blowing when you think about it like that. Okay, moving on. Then there's borosilicate glass. Many people might recognize this as the brand name Pyrex in their kitchen, or they see it used for laboratory glassware like beakers and flasks. What makes borosilicate glass special, particularly when it comes to handling extreme temperature changes?
Borosilicate glass stands out primarily because its chemical recipe includes a significant amount of boron trioxide, usually somewhere between 8 and 15%, replacing some of the soda and lime found in standard soda lime glass.
Boron.
And the crucial property that this addition of boron imparts is a very low coefficient of thermal expansion.
Low thermal expansion. What does that mean in practice?
It means that when borosilicate glass is subjected to rapid or extreme changes in temperature, think about taking a glass baking dish from a freezing refrigerator and putting it directly into a preheated hot oven, or heating a scientific beaker directly over a roaring Bunsen burner flame. It expands and contracts very, very little compared to regular glass.
So it doesn't stress itself out when one part gets hot or cold quickly.
Exactly. Because it doesn't expand or contract much with temperature changes, it doesn't generate those dangerous internal stresses that cause regular glass to crack or shatter under thermal shock. This makes it incredibly resistant to breaking due to sudden temperature variations.
Which is a huge safety feature, preventing dangerous shattering or even explosions in high heat environments like kitchens or labs.
Absolutely. It's why it's the go-to material not only for ovenware and laboratory glassware, but also for many industrial applications involving high temperatures or thermal cycling, like certain types of chemical processing equipment, high-intensity lighting fixtures like halogen lamp envelopes, and even the massive mirrors used in large astronomical telescopes, where maintaining shape despite temperature fluctuations is absolutely critical for optical precision. It's really the workhorse material for applications demanding serious thermal resilience.
Makes sense. Then we have tempered glass. Now, this is distinct from chemically strengthened glass like Gorilla Glass, right? Although they both sound strong. I know tempered glass is used often in car side windows and maybe shower doors. How is it made differently?
Very distinct indeed, although you're right, both processes aim to significantly enhance the glass's strength. Tempered glass, unlike Gorilla Glass, is strengthened through a purely thermal process, not chemical.
Thermal.
After the glass, usually standard soda lime float glass, is cut to the final desired size, and any necessary holes are drilled or edges finished because you can't cut or drill it after tempering.
Oh, good point.
It's heated uniformly to a very high temperature in a special tempering furnace, typically around 700 degrees Celsius. about 12,292 Fahrenheit, which is just below its softening point. Then, the crucial step, it's immediately and rapidly cooled, or quenched, by blasting jets of cold air onto both surfaces simultaneously.
It's a really fast cool down, the opposite of annealing.
Exactly the opposite. This rapid quenching causes the outer surfaces of the glass to cool down and solidify much, much faster than the interior core of the glass, which remains hotter for longer.
Okay, so it's also about managing stress again, but this time inducing it deliberately through rapid cooling rather than removing it slowly or using chemical exchange. What's the key property this gives the glass, particularly when it breaks?
Yes, it's all about inducing a specific controlled stress pattern. This rapid cooling process creates a layer of intense compressive stress on the surfaces, similar in effect to the chemical strengthening. But simultaneously, it creates a balancing tensile stress within the inner core of the glass. This combination significantly increases the overall strength of the glass. Tempered glass is typically 4 to 5 times stronger than regular annealed glass of the same thickness.
4 to 5 times stronger.
Yes. But perhaps its most vital characteristic, the reason it's considered a safety glass, is how it behaves when it does eventually break. Because of those high internal stresses locked inside, if tempered glass is impacted hard enough to fracture, it doesn't break into large, dangerous, razor-sharp shards like annealed glass does. Instead, it shatters completely, almost explosively, into thousands of small, relatively harmless, blunt, pebble-like pieces.
Which is why you often see those piles of tiny glass cubes or pebbles on the road after a car side window gets broken.
Exactly that. You don't see massive, dangerous glass knives sticking out. It crumples into tiny, much less injurious fragments, making it ideal for applications like car side and rear windows, glass shower doors, sliding patio doors, and even things like glass backboards for basketball hoops.
Fascinating. Okay, and finally, laminated glass. This one sounds like it's built differently again, maybe for serious impact resistance and actually holding together.
Laminated glass is indeed designed for maximum safety, security, and also sound insulation. It's constructed very differently. It's made by sandwiching one or more layers of a flexible plastic film. Typically, it's a tough, resilient plastic called polyvinyl butyryl, or PVB. But sometimes other materials like ethylene vinyl acetate, EVA, or specialized resins are used permanently between 2 or more layers of glass.
So glass, plastic, glass, like a sandwich.
Exactly like a sandwich. These layers are bonded together under heat and pressure in a specialized oven called an autoclave. The key property here is that when laminated glass is shattered by an impact, the glass fragments adhere firmly to that tough plastic interlayer.
Like car windshields. I know when a rock hits your windshield, it cracks and makes that spiderweb pattern, but the glass doesn't usually fly into your face.
Precisely. Car windshields are the prime and legally mandated example in most places. The glass cracks, but the interlayer holds the broken pieces together, maintaining the integrity of the windshield, preventing dangerous shards from flying into the passenger compartment, and also maintaining a barrier against the elements or objects from outside.
Right.
But laminated glass is also widely used for safety glazing in buildings, particularly in overhead skylights, glass railings, storefronts, and windows in schools or hospitals. It's also the basis for bullet-resistant glass, which uses multiple layers of glass and plastic, and hurricane-resistant windows. Basically, it's used anywhere where security, sound reduction, the plastic layer dampens sound well, or preventing glass from falling out of its frame when broken is paramount.
Okay, so if we connect all this back to the bigger picture, these specialized types of glass, Gorilla Glass, borosilicate, tempered, laminated, they truly show how material science is continually pushing the boundaries of what this seemingly simple material, glass, can actually do. From our everyday phone screen surviving drops, to lab equipment handling intense heat, to critical safety barriers protecting us in cars and buildings. Glass is being meticulously engineered to address very specific needs for durability, safety, thermal resilience, and optical performance in ways that people centuries ago could probably never have even imagined.
Absolutely. It's not just a single material anymore. It's really a versatile family of advanced materials, tailorable for almost any conceivable purpose. It's quite remarkable.
And as we start to wrap up our deep dive into this truly fascinating world of glassmaking, we really need to come full circle back to a topic we touched on earlier, but one that honestly deserves its own final spotlight: the incredible power of glass recycling. Because glass is truly one of the most sustainable materials we have, primarily because it's 100% recyclable with virtually no loss of quality, and it can be recycled indefinitely.
This is perhaps one of the most compelling and positive aspects of glass as a modern packaging and building material, and it's a true triumph of implementing a circular economy. Unlike many other materials, like some plastics or paper, which tend to degrade in quality or become unusable after just a few recycling loops,
Right.
glass can be melted down and reformed into new glass products over and over and over again, theoretically forever, without any significant degradation in its structural integrity, its optical clarity, or its chemical properties. A recycled glass bottle can become a brand new glass bottle, or a window pane, or glass fiber with exactly the same performance characteristics as if it were made entirely from virgin raw materials.
That's incredible. Indefinitely recyclable. And the benefits of using that recycled glass, the cullet we talked about, are immense, aren't they? Not just environmentally, but also economically for the manufacturers themselves.
They really are substantial on multiple fronts. Firstly, as we discussed earlier, there's a very significant energy saving. Recycled glass, the cullet, melts at considerably lower temperatures than the raw virgin materials, sand, soda ash, limestone, because it's already undergone that energy-intensive chemical transformation to become glass in the first place.
Right. The pre-cooked meal analogy.
Exactly. This directly translates to significantly less energy needing to be consumed during the melting process, which, remember, is by far the most energy-intensive part of glassmaking. The general estimates suggest that for every 10% of cullet used in the furnace batch, there's about a 2 to 3% energy saving. Now, when you consider that many modern glass factories routinely operate with levels of 80%, 90%, or sometimes even higher percentages of cullet, those energy savings become truly staggering. We could be talking about reducing the furnace energy consumption by 20, 25, even close to 30% compared to using only virgin materials. That's huge.
Wow. So much less energy needed, which directly translates to a significantly smaller carbon footprint for the whole process.
Yeah.
And beyond just energy savings, there must be massive resource conservation benefits too.
Absolutely. Using cullet extensively reduces the demand for extracting virgin raw materials like that high purity silica sand, the soda ash, which is also energy intensive to produce, and the limestone. This directly lessens the environmental impact associated with mining and quarrying these materials, things like habitat disruption, water usage, and the energy used in transportation. And of course, tied into the energy savings, there's a significant emission reduction. Lower melting temperatures mean reduced greenhouse gas emissions, particularly CO coming from the combustion of fuel in the furnace. It also means less emission of other air pollutants like NOx and SOx, and less particulate matter. And quite simply, recycling glass dramatically reduces the volume of waste that would otherwise end up going into landfills, closing the loop completely on the material's life cycle.
So what does all this mean for us, the individual listener at home? It really means that when you take the time to toss a glass bottle or jar into your recycling bin, you're not just doing some small symbolic favor for the environment. You're actively participating in an incredibly efficient and beneficial industrial process that embodies the very best principles of the circular economy. You're directly contributing to massive energy savings, significant conservation of natural resources, and real reductions in pollution on an industrial scale every time you recycle displays up.
Precisely. It really highlights glass as a fantastic model for other industries in terms of its almost perfect, indefinite recyclability and the significant tangible benefits that using recycled content, cullet, brings back to the entire manufacturing process. From an inherent material property standpoint, it's a truly sustainable material as long as we do our part in the recycling chain.
So there you have it. That was our deep dive into the truly fascinating, surprisingly complex world of glassmaking. From that humble yet carefully selected high-purity silica sand, meticulously combined with precise chemical modifiers, and importantly, often a very large percentage of recycled material, to the intense, almost alchemical heat of the melting furnace, the incredibly ingenious shaping processes like floating on tin or blowing into molds that almost defy belief, and then that critical, slow annealing process for strength. Every single step we discussed is a testament to literally thousands of years of human innovation, a profound scientific understanding of materials, and incredibly meticulous, often automated craftsmanship.
It's amazing, isn't it? What appears to us as just a simple, clear window pane, or the bottle holding your favorite beverage, or maybe the incredibly tough, smooth screen on your phone, is actually the end result of incredible precision, a deep understanding of chemistry and physics at extreme conditions, and continuous technological advancement over centuries. It's a clear, often beautiful, and truly incredibly engineered material that has fundamentally transformed the world around us in countless ways, both visible and invisible.
So maybe the next time you interact with glass, whether it's looking out a window, watching the world go by, checking your phone for a message, raising a glass in a toast, or just admiring the light through a vase, perhaps pause for just a moment. Take a second to truly consider the intricate, ancient, yet highly precise and energy-intensive journey that piece of glass undertook to get from the earth, through the fire, and into your hands. What new appreciation do you now have for this transparent, beautiful, and incredibly engineered material? We hope you'll never quite look at glass the same way again.
It really is hidden complexity in plain sight.
Join us next time for another deep dive, where we'll explore the hidden wonders and intricate workings of another fascinating aspect of our world.